It is crazy what math emerges from the most everyday items. Take toilet paper, for instance. If you're in the 30% of the world population that has regular access to toilet paper, then it's something you've probably used thousands of times and also probably not thought much about. However, that's not the case of astute commentator at CFSSHK, who was wondering if the toilet paper roll decreases more quickly when it is small compared to when it is large. Or does it just seem that way? Here's another toilet paper quandary you might have wondered about while in the public bathroom with 2 rolls of toilet paper. Which one should you use, the big one or the small one? Well, we'll look at what happens at the rolls if there are more big choosers, people that use the large roll, or small choosers, people that use the small roll. Which one should you be? And I will tell you it does matter because your choice impacts the probability that someone's going to be left on the pot with nothing but an empty tube. Welcome back to Math the World. If you haven't already, subscribe to our channel and please like, comment, or share this video. Our mission is to show how math can be used in all kinds of real-world contexts, and we want to share that with the world. We have 2 toilet paper questions to address today. First, how fast does that toilet paper roll shrink when there are different amounts of toilet paper left on the roll? Second, what happens to the rolls of toilet paper when there are 2 options to choose from, and some people take from the bigger roll and others from the smaller roll? Let's start with question 1. I actually first started to do this problem by modeling the layers of toilet paper by an Archimedean spiral in polar coordinates, but realized I could analyze it much more easily if I thought of using up toilet paper as removing area from the washer-shaped end. We can do a simple analysis to start with in order to convince ourselves that the radius of the roll will decrease faster when the roll is smaller. Let's look at the end of the roll. Suppose that the amount of paper we use in one sitting is enough to go 3 times around the roll when the roll is large. How many times will the amount go around the roll when the radius is half as big as that? It'll go around 6 times. So we're taking off layers twice as fast when using a roll that is half as large. So at CFSSHK, you are correct. The layers of TP do seem to vanish more quickly when the roll is small. Let's see what insight we can gain by a more comprehensive analysis. We can use related rates, which is a calculus technique, to better understand the situation. Why related rates? Or why calculus? Well, we're interested in a rate, the rate that the radius of the roll is decreasing. So that's a clue that differential calculus could be a good tool for us. In calculus notation, we could write the rate that the radius of the roll is changing as dr dt, the change in the radius with respect to the change in time. Related rates will help us develop a formula that relates r and dr dt, or in other words, the radius and how fast the radius is changing. What are the other quantities in this situation? We have the area of the end, which we'll call A, and we have the amount of toilet paper we use each day, which we will call P for paper, because I will be using the letter T for time. For the units of A, we will use centimeters squared. But what are the units of P? The amount of toilet paper we use each day? Well, we could start with the length of toilet paper. That seems natural, so P could be in centimeters. But P is actually a rate. It's how much we use per day. So we should actually measure P as centimeters per day. However, we really need to convert the length we use each day, P, into an area so we can connect it to the area of the end of the toilet paper roll. To turn the length into an area, we need a thickness, which we will call K, and multiplying the thickness by the length gives us an area. This makes sense if we lay out the average length of toilet paper that we use in one day onto a flat surface. Then the area of the edge is a long, thin rectangle. The area will be the length times the thickness. As long as we measure the thickness in centimeters, then K times P will be units of centimeters squared. So K times P is the rate that the area of the end of the toilet paper roll is decreasing each day. We can write that succinctly as dA dt, although since it is decreasing and K and P are positive, dA dt equals a negative Kp. Now that we have all of the pieces, let's put them together. The relationship between radius and area is area equals pi r squared. This equation can be used to find the area of a circle if we know the radius, or the radius of a circle if we know the area. But our main question is about rates. The related rates technique can be used to create a different equation, one that connects the rates at which the quantities are changing, not just the values of the quantities themselves. Many students learn to use implicit differentiation for related rates. If we implicitly derive the equation assuming that area and radius are changing with time, then we get this new equation, dA dt equals 2 pi r dr dt. Now we can substitute a negative Kp for dA dt and solve for dr dt. The reason we're solving for dr dt is because That's the quantity we're trying to understand, the rate at which the radius changes with respect to time. We find that d r dt equals a negative kp divided by 2 pi r. So what does this tell us? As we analyze this equation, it helps to confirm our intuition about the situation. Since kp and r are all positive, d r dt will always be negative. This means that the radius of the toilet paper is always decreasing, as it should be. We can also see the rate that the radius decreases is proportional to k and p. So if you buy toilet paper that's twice as thick, you'll use up toilet paper twice as fast. That is assuming you still use the same number of squares with a thicker toilet paper ply. Or if you double the amount you use each day, which is the value of p, then you also use up the toilet paper twice as fast. Nothing surprising here. What about the radius? Well, the rate is inversely proportional to the radius. So when the radius is half as much, the radius is decreasing twice as fast. When the radius is 1/3 as large, perhaps 1/3 as large as a new roll, the radius of the roll is decreasing 3 times as fast. I looked up some reasonable values online to see how fast the toilet paper roll is decreasing when it gets down close to the tube. It's going down at a rate of almost 4 millimeters a day. So there we have it. As you get closer to the end of the toilet paper roll, the radius of the toilet paper does indeed decrease more quickly. Now let's move to our second question. For this one, we have 2 rolls of toilet paper, a big roll and a small roll. What happens when some people choose the big roll and others choose the small roll? Is there one you should always choose? Well, this situation was analyzed by Donald Knuth, a Stanford professor of computer science and mathematics, back in 1984. Dr. Knuth is known for his work in analyzing algorithms and creating TeX, the computer typesetting system for mathematical expressions. For the 2-roll toilet paper problem, he used an analytical approach. It's beyond what we can get into today with the use of recurrence relations, special power series, Catalan numbers, and generating functions. So instead, we can go the easy route and write up a simple simulation in a spreadsheet. But first, let's get a good understanding of the situation. Let's assume there are 2 rolls, one with 40 portions and one with 20 portions. If a big chooser comes in, they use a portion on the larger roll. So now we have a roll with 39 portions and a roll with 20 portions. Suppose a small chooser then comes in, they would use one portion on the roll with 20, so we were down to 19 on the small and 39 on the large. If the rolls have the same number of portions, then they could choose either one, and we could just pick one at random. So we have a pair of numbers that decrease until one hits 0. What we want to understand is how many portions are left on the other roll when one runs out. That's important because too few portions on the single roll left means it can run out before the toilet paper can be restocked, which is not a situation anyone wants to be in. The 2 extremes are easy to handle without a simulation. If everyone was a big chooser, then the larger roll gets used up until it's equal to the smaller roll. Then one roll is randomly chosen, the next person would use the larger roll and get them back to even. So eventually the rolls are 1 portion to 1 portion, so when one runs out, there's only 1 portion left on the other. Seems like a worst case scenario. If everyone was a small user, then the small roll is used up first and the large roll still has all of the portions on it when the first roll runs out. That seems like a best case scenario because the empty roll can be replaced with a brand new one. This is the logic behind the dual paper roll design in public bathrooms, where one roll can't be used until the first roll is almost used up. So what happens in between? What if there are 80% big choosers and 20% small users? Or 70-30 or 60-40? This is where the simulation can help us. I created the simulation and started with 100 portions on each roll, and ran the simulation for different probabilities of big choosers from 100% to 0% in jumps of 10%. For each probability, I ran the simulation at least 500 times and found the average number of proportions left on the remaining roll when the first one ran out. This was our result. Notice that if there are 50% or more big choosers, there aren't that many portions left, on average once one roll runs out. But if you can go 40% big choosers, 60 small choosers, it starts to make a big difference. But look what happens as we push the percentage of big choosers lower than 50%. Then the amount of toilet paper left on the remaining roll increases substantially. Donald Knuth came up with the same result with his analytical approach, and you can see that our chart actually matches quite closely to his graph. So what does this mean? It means choose the small roll. You might be the person that saves that poor soul from being left without enough toilet paper. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.